My name is Thomas Rush. I'm the founder of QuickBlocks.io. I'm going to discuss our C++ software library called QuickBlocks. Our goal, which is reflected in our name, is to deliver ultra-fast, fully decentralized, rich blockchain data to the UI of your decentralized applications. In our first iteration, we were querying in Fura and using the Web 3.0 JavaScript library. We found this method to be inadequate for two reasons. First, it was too slow, and second, Infura is centralized. The dotted gray line represents the boundary between a centralized world and a decentralized one. Our next obvious step was to move the Ethereum node locally. This greatly increased the speed with which we could query the data, but now we realized we had a more difficult problem. The blockchain data is organized wonderfully for a blockchain. It's not organized well at all for accounting, and we think for a full-featured DApp. And this is where QuickBlocks comes in. QuickBlocks still uses the RPC, but instead of delivering the data directly to the DApp, we pre-process it and extend it so it delivers the data we want it to. Furthermore, we store the data in a standard Web 2.0 database. This allows the DApp developer to leverage existing web development skills and platforms. It also allows us to deliver a richer stream of data and to do so much more quickly than we could by querying the node. Let's look closer at what we're actually doing. Initially, we simply asked the node to give us the blocks, and we stored them as JSON files. In addition to taking up a huge amount of disk space, this required us to parse the JSON, which, while it was faster than querying the node directly, is still way too slow. So we moved to a proprietary binary format. During this process, we found that nearly 40% of the blocks contain no transactions. So in addition to storing it as binary, we eliminated all the empty blocks. But we still had to parse the data due to the variable number of transactions in each block. In our next iteration, we separated the transactions from the blocks, and this is where we are now. Next, we plan to store this data in a proper database, and at that point we'll be able to deliver fast per account data to your DApp at web scale speeds. A quick reminder of our goal is fast, full-featured, decentralized data to your dApps. So let's look at some results. This is a simple example of our code. First, you can see that you would call this function in our library for every non-empty block. This function takes a function pointer as an argument and also takes a pointer to an arbitrary data, in this case a counter. Note that this data can be as complex as you like. This is the function that you would provide as the pointer, and it gets called with each encountered block along with the data that you provided. And here we're accumulating the number of transactions in each block into the counter. Finally, we print the result to the screen. Note that by default, we visit every block, but you may specify a starting and an ending block, and I'll explain why this is interesting in a moment. In this screen, we show results. First, you can see that we compared the various methods, going to parity, going to the binary files, and finally to our database. We visited 2.1 million blocks and nearly 9 million transactions. In the process, we encountered 5.12 quadrillion and in those 9 million transactions. And here you can see that parity through the RPC, even though we only fetched 50,000 blocks, was only able to attain 425 blocks per second. The two binary methods reached about 2,500 blocks per second, and our database method reached up to 30,800 blocks per second, or nearly 130,000 transactions per second. Returning now to our presentation, where do we go next? We've already started working on an account index, which will list the first encountered block and the most recently encountered block for each account. We found this only takes about 50 megabytes of data, believe it or not. This will allow us to skip over the whole chunks of the blockchain while we're searching for per account data. Only when your DApp asks for a per account data for a particular address will we spin through the chain looking for transactions for that account. This will take some time, but we will cache that data, making future references or future requests for that same data significantly faster. At the same time, we can enhance that data by marking transactions in error, checking the out of gas condition, And we can also search for internal transactions to or from smart contracts, neither of which the RPC makes easy to get to. We can also parse the smart contracts input data field to extract the functional parameters, as you can see in the example I'm going to mention in a minute. In the long term, we want to provide a way to verify that our data is identical to the data you'd get from Web 3.0. We're looking into how we might be able to store this data on IPFS or IPDB. And there's an example at DAO.QuickBlocks.io. Thank you for listening. We hope you found our presentation interesting. If you have any questions, please contact us through our website at QuickBlocks.io. We'd be happy to answer any and all questions you may have. Thank you and goodbye.